everybody. If you're watching this, you missed day 2 of our week 6 computer science principles lecture. Let's get going. So today we had a shortened class period, so we couldn't do a whole lot. We mostly focused on going over the assignment from the asynchronous day, so I'll do that a little bit here, but of course I won't be able to address your particular concerns if you have some, so make sure you email me if you have issues or questions. We also talked about something called the halting problem and also parallel and distributed algorithms. So let's get started. Please don't forget, if you owe me assignments, they're past due at this point, so make sure you turn your stuff in. All right, the halting problem. I highly recommend you go to MyMCPS, click on modules, week 6 slides, and watch this video. It explains the halting problem in a lot of detail. And the idea is you can't have a machine that basically determines if a particular problem can be solved by a particular machine, because logically that machine would be able to determine if it itself would be able to solve the problem, and if you were to combine that with a machine that negates the output, it just wouldn't work. Now, the explanation really was probably confusing and didn't do it justice, so watch the video. The video explains it quite well. If you still have questions, send me an email. But essentially, the important takeaway here is there are some problems that no computer will ever be able to solve. We know this for a fact. We have proven it logically and mathematically, and we call those problems undecidable. So this is kind of the conclusion of our discussion of various algorithmic complexities. You have problems that a computer can easily solve, problems a computer can solve with some effort, problems that a computer could in theory solve, but it takes so long, we just say, let's not bother. We call those intractable problems. And last but not least, we have these undecidable, something that a computer could never, ever, ever solve. Alrighty. Now let's talk about algorithmic complexity really quickly. So some things that kept coming up during our discussion is, first of all, keep in mind that when we're talking about algorithmic complexity, O of 1 simply means any number of single instruction lines. So what do I mean by that? Because we only care about how fast the computation grows, we don't really care about any lines that don't change as the input increases, right? You can have lots and lots of lines of code that always happen, but if it's a consistent number, we don't really want to count those in our big O calculation. So an example would be console.log or an if statement or, I don't know, a variable assignment, etc. Any of those don't really count. They're just a single line. You can disregard them, and if that's all you have, your big O is just big O of 1. Big O of n has a traversal of some data set. We only know about lists really as a data set, so this is going to be a list for us. Where I equals 0, I is less than list.length, I++. That is big O of n. It's going to go through every element in the list. We say the list has n elements, therefore big O of n. All right, now let's look at big O of n squared. So that would be 2 of these guys right here. So you'd have an outer list, and then, or rather, an outer loop, and an inner loop. And of course, we'd have to use a different letter here, so maybe J. So if we were to do this, now we have n traversals that we have to do for this outer loop. And for each of those, we have to do n traversals for this inner loop. N times n is n squared. Hopefully, all of that makes sense. Last but not least, logarithmic. So O of log n. Well, this occurs when you increase your counter by either multiplying or dividing it by some number over and over again. So for instance, an example would be var I equals list.length. I is got to be greater than 1. And we're going to say I equals I divided by 2. Well, what's going to happen here? Well, every time we run this, we're going to divide the list length by 2. So the number of times this runs is equal to log 2 of n. what power do we have to take 2 to get the length of the list? That's the question we're trying to answer. So this is obviously much faster in terms of how long it'll take to run. So we try to strive for that time if possible. Now, certain things you can't do this way, right? In fact, most things we've done in this class you can't really use this form for. So there you go. That's basically all you need to know for big O times. If you have any further questions, please make sure you send me an email. All right. Last but not least, we're going to talk about sequential versus parallel computing. So we are really, in this class, doing mostly sequential computing. All of our lines of code happen one after the other. Now, we are doing some event-driven programming, which is a little different. We're not doing any parallel computing. And parallel computing involves taking a task and having multiple cores or multiple CPUs work on that task simultaneously by doing different parts of it. Now, obviously, not everything can be done in parallel. Some things you have to wait for. So, for instance, let's say you're packing up to go on a trip. Your parents can all pack their own bags. If you do that, that's a task you're doing in parallel. No one has to wait for anyone to do that task. Once you're all packed, you have to put your bags on the car. You have to wait for your parents to put their bags in the car before you can put your bags on the car because that's the way they have to fit in. So there's no way to do that task in parallel. It's one car that you're loading. So that would be a sequential task. Because of that, there's different amounts of speed up you can get depending on how much of your actual program you can do in parallel, how much has to stay sequential. So what does that mean? That means that we have this idea here. It's called Amdahl's law. As the number of processors increases, the speed up you get is really going to depend on how much of your task you can do in parallel. If it's just 50%, you're going to see very diminishing returns very quickly. If you can do a lot, like 95%, you can get quite a bit of speed up. Speed up is just found by taking the amount of time it would take you to do the task normally and dividing it by the faster time using the parallel computing. Now, most tasks in real life can't be 95% parallel. You have to have some sequential steps in there that are just not possible to remove. So most things are going to live over here somewhere, maybe around this red line, which is why 8 cores is usually plenty for most computing. That's pretty much everything. Now, you do need to know about these terms here, and we're going to talk about distributed computing next time. Thank you very much. If you have any questions, send me an email. I hope you have a fantastic weekend.